The last time we established the idea of momentum, which is p, and it's a vector quantity, and it's just m times v, the mass times the velocity. Well, we also established that in an isolated system, like two cars moving towards each other, that the momentum is conserved. So the total initial momentum is equal to the total final momentum. But this is only for an isolated system. And isolated means that there's no external forces. So if there's no external forces, that means forces from the environment acting on the system, then we have conservation of momentum. Now, in the practice set, you dealt with some problems where momentum was not conserved. In other words, the initial momentum was not equal to the final momentum. So for instance, if our system, this is one ball, it's not two different balls. So this ball is flying towards a wall, it bounces off and comes back. I drew it down here on the way back because it gets messy drawing it on the same linear. But the ball comes in, hits the wall, bounces back in the opposite direction with the same magnitude. So we could just say that the magnitude v naught, or the speed, is equal to the final magnitude. So at first you may think that momentum's been conserved, but you have to keep in mind that velocity is a vector, and so it's changed directions. And because of that, it's not the same. So if we write this out, the momentum to begin with is mass times v naught, and then the momentum after is going to be mass times negative v naught. Because again, they're the same magnitude. So the negative v naught. So they're the same magnitude. And so mv naught is not equal to negative mv naught, clearly. If we move this over though, then we get the mass of the velocity initial, and that would be plus the mass of the velocity initial, is equal to some change in momentum. And so this would be 2 times mv naught would be our change in momentum. So the momentum, we've had a double in the amount of momentum, or the change in momentum is twice the initial momentum. Anyway, this is what we want to get to, is this change in momentum. That's what's key. So if momentum's not conserved, then we have a change in momentum. It doesn't matter, I went through this to just kind of build up this idea. So there's a change in momentum in this case. And if we think about it, it's easy to figure out where it came from. And it's the force over here on the wall. So the wall is acting on the ball, and the wall is out here in the system. So we have an external force. And that's the whole point of this discussion. We have an external force acting on the system, and it causes a change in momentum. So if we have a change in momentum, so I'm going to shift gears and go through some derivations real quick. So if we have a change in momentum, then that implies that we could just subtract the final momentum minus the initial momentum. And we're just looking at a single object in our system. So our system would be, some object with mass. So if there's a change in momentum, it's because there's an external force acting on it. Okay, so the change in momentum, final momentum is just the mass times final velocity minus mass times the initial velocity. And if I factor out the m's, I get m times vf minus v naught. And this part right here, vf minus v naught, leads me into acceleration. So I have some acceleration. I've had a change in velocity. The mass hasn't changed. So it's all in the velocity. Now we can have cases where the mass changes, and that will change our momentum. But for now, we're just going to think about the velocity. So if I had a velocity change, that means that there's acceleration. So now let's go over to 2 of our definitions for acceleration. So we have acceleration. The definition is the change in velocity, or vf minus v naught, over the change in time. And I'm just going to write it as delta t. And we also know from Newton that the acceleration is just the net force divided by the mass. That's Newton's second. So the definition of acceleration, Newton's second law. However, these are both acceleration, so we can set this one equal to this one. So we get Vf minus V naught over delta T is equal to the net force divided by the mass. And then if I multiply this over, I get mass times Vf minus V naught is equal to, and multiply this one over, the net force times delta T. Now, if you recognize this part right here is that, which is my change in momentum. So let's go ahead and rewrite this. So my change in momentum here is going to be the net force times delta T. And this quantity right there, that is what we call impulse. And so we're going to use a J for impulse. And this is a vector quantity because of the force. Force is a vector, so impulse is a vector. So we'll define impulse to be our change in momentum. So this is impulse. And impulse is defined as the net force over time, times time. How long are you pushing it, and how hard are you pushing it, and for how long? And that determines our impulse, which will in turn determine our change in momentum. It kind of just makes sense. So if, say, let's do a quick example, maybe it makes sense. So if you have an object, let's just do this, a big mass moving towards you at some velocity, say v. And when it reaches you, you're going to push on it, with a certain amount of force for a given amount of time. By doing so, you're going to accelerate this thing. You're going to turn it around and maybe make it go back the other way, or you're going to stop it. So let's do that. So what's going to happen if we just stop it? So when you catch a ball, you have a ball moving in with some velocity, and over a certain time period, you apply force to stop it. So the initial momentum is going to be mv naught, and the final momentum would be 0 because we stop it. So how much force if we had a time, that sort of thing. So what we would start is that, well, our change in momentum is defined as the impulse. So the change in momentum would be the final momentum minus the initial momentum equals impulse. And impulse is just going to be your average force times delta T. So working here, our final momentum is 0. So we just get negative m v naught is going to be your average force times delta T. Moving this over, you get the force, the average force is going to be negative mv naught over delta T. So that's how we would get our average force. I'm just walking through to kind of see, you can start to make some connections between this. But notice this negative sign. So it says that if my velocity is positive and I stopped it, then my force has to be negative, and that matches my picture. My velocity in this case, if we define that way to be positive, then the force has to be negative in order to stop it. And this leads us to something else that's interesting. Newton's second law, we can rewrite it. So if the net force is equal to the mass times the acceleration, then net force mass, acceleration is your change in velocity over time. Sorry, got a frog in my throat. So the net force is going to be mass times change in velocity over the change in time. So the net force is equal to the change in momentum. This is one way of going through the derivation over time. This is Newton's second law in terms of momentum. Newton second with momentum. And this is the way he actually talked about it. So if you go back and read what he wrote when he was deriving the laws in the Principia de Mathematica, he talked that his second law was actually in terms of momentum and not acceleration, momentum over time. So momentum is a big idea that we can deal with. And this is showing Newton's second law. So you just have a change of momentum up here divided by time, and that's your force. That's what this is showing. This also comes straight out of the definition of impulse, this right here. So you see, if I just divide the delta t over, I get net force as change of momentum over time, which is Newton's second law for momentum. Just keep in mind that the force, this has to be an external force. And we talk about an average force. We can see this on a graph. So graphs. So if we graph force over time, you can determine the velocity off of this thing. So say I apply a constant force for some time period, say, I don't know, 3 seconds. So 1, 2, 3 seconds. I apply some force, I don't know, 3 newtons of force. You could ask, what's the final velocity? Well, since it's force in time, we know that force times time is equal to the change of momentum. And assuming an initial velocity of 0, then my force times delta t would just be the final momentum, or mvf. And so this part, the impulse, well, that's going to be the area under this curve. So this area right here, the area on a force versus time graph equals the impulse. So to get this value, I just find this area. So it would be 3 times 3 is 9. So I would get 9 mvf. And then to find the velocity, just divide by mass. And there you go, there's your final velocity. So know this, just keep in mind it's delta t. So for instance, let's do another one. If I had a graph, and I'll draw it in red. So we don't apply a force, and then all of a sudden it spikes, and we apply a force over some time period, and then we go back to nothing, no force, average force. Let's say this is 2 newtons, and this was from 2 to 5. Okay, so to get the impulse here, this is force over time. Impulse is going to be the force times delta t. So when we multiply, that's area. So we would get, the length here would be 2 newtons, and the length here. So you can see it's the change in time, so it'd be 3. So we get an impulse of 6. And those are, the units on these things are going to be the same as momentum, so kilogram meters per second. Okay, so that's impulse. Now, how does this all tie into collisions? So I'm going to go back to the collisions that we did last time so we can think about that and see what's actually happening. So suppose I have 2 cars moving at each other, and they're going to collide. So this one has velocity, this one has velocity. I don't know what the masses are. But these things are going to collide and bounce off. Now we learned in an isolated system, so if I have a system of these 2 cars, that momentum's conserved. But what if I just have one? So what if I just analyze one car? So if we say cart 1. So here, let me isolated 2-cart system. We've already established that the momentum is conserved. So the total initial momentum is equal to the total final. And I'll expand this out. So the initial, for this situation, it would be m1 v1 naught plus m2 v2 naught is equal to m1 v1 final plus m1 M2 V2 final. So these are just all the momentums here dealing with this. So we know it's conserved. Okay, but now we're going to look at just one cart. So cart 1. So cart 1 has some initial momentum. So we're going to have M1 V1 naught. And then it's going to collide. And, you know, let's suppose it doesn't matter, but there's going to be some new velocity afterwards. And because there's a new velocity, that means that there is a change in momentum. And so we're going to have an impulse. You know what? Actually, let's go back. Let's write this a different way because we don't have the impulse momentum. We'll do that next time. So this velocity is going to change. So we have a change in momentum for 1. And that, of course, is going to be the impulse on 1. So the change in momentum would be the mass 1 V1 final. Remember, it's always final minus initial. Mass 1 V1 naught is equal to impulse is the force times delta T. And this would be the force. The force that's changing it is going to be 2 on 1. 2 on 1. So the force of cart 2 on 1 is what's changing it. Let's go to cart 2. So for cart 2, we're going to get a change in momentum on 2 as well. And that would be the impulse on 2. And likewise, so we get mass 2 V2 final minus mass 2 V2 initial is equal to the force of, and the force changing this thing when they collide is going to be the force of 1 on 2. So we get the force of 1 on 2 times delta T. Now these things, the delta T is the same for both because they're in contact for the same amount of time. And if we look, these forces here, so the force of 2 on 1 and 1 on 2, 2 on 1 and 1 on 2, well, that's Newton's third law. So we could say that the force of 1 on 2, either way, so the force of 1 on 2 is equal to the negative of force 2 on 1. That's Newton's third. So equal magnitude, opposite directions. Those are the forces pushing on each other. So now we can make some substitutions. So the mass 1 V1 final minus, which one am I changing? Let's change this one, sorry. It doesn't matter, but the way that I wrote it, let's just follow through. So we're redefining the force of 1 on 2 as negative force 2 on 1. So we get all of this stuff is going to be equal to negative force 2 on 1 times delta T. And that would be mass 2 V2F minus mass 2 V2 naught. Okay, what I'm trying to do is make this look like this, and then we can set them equal to each other and get rid of the forces. So I can multiply everything by negative on this side. So I'm going to rewrite everything. So force of the 2 on 1 delta T is equal to multiplying everything by negative flips the order of these. So we get this one positive, mass 2 V2 naught minus mass 2 V2 final. Now we have this, and these are the same things. Therefore, this equals this. So now we can pull these together. So we get mass 1 V1 final minus mass 1 V1 initial is equal to this stuff. Mass 2 V2 naught minus mass 2 V2F. Gathering our initials and finals together. So I would move this one over here. So I get mass 1 V1 final plus this. So plus mass 2 V2 final equals mass 2 V2 initial plus this plus mass 1 V1 initial. So what you can see is that this is the total final momentum is equal to the total initial momentum. So you can see that even using impulse, if we if we take the systems and then put them together, we can still recover that momentum is conserved for both of these carts. So it all just depends on the system that we define. If we do one, then we have an impulse. If we do both, momentum is conserved. There's no impulse because all the forces are inside and they'll wash out because of Newton's second law. So that's impulse. I'll give you some problems and we'll be good to go.